Hi, class. All right. We left off talking about trig substitution, and I'm going to keep talking about trig substitution for, I believe, 4 more examples. My goal here today is really just to give you a lot of different types of things that you might encounter, whether it's with trig substitution or with any sort of integral that might have a trinomial in it, which we're going to talk about in 7.4. So I'm going to remind you, though, we were given some formulas for trig substitution. We worked with one of them in example 1. It was the square root of a squared minus u squared. Remember that we're just looking for this form under the radical in the integral. And if you see one of these forms, you can go ahead and set up the substitution just the way it's listed. You don't have to prove anything, derive anything. You can just choose whatever u is, which is the quantity that's being squared, and set it equal to a, which is also the quantity that's being squared for your constant, sine theta in that instance, so on and so forth. Your triangle's there if you need it. We had some similar rules for if we had a squared plus u squared under the radical, or u squared minus a squared under the radical. So noting that these two are different scenarios here where the order of subtraction is switched. So the example that we did, example 1, was in the form a squared minus u squared. So we isolated a, we isolated u, and then we set up the substitution, remembering to sub out the dx, and then we went through and used that process of integrating trig functions in order to arrive at our conclusion here at the bottom. Okay. Excellent. So let me give you example 2. My goal here today is to give you 4 more trig substitution examples and then move into 7.4. Now, 7.4 is going to include some review in it, but it's also going to kind of expound a little bit further on some forms for which you might see a trig substitution. So we'll get there. We'll see it. Oh, noting the time. I think I started. Okay. Because I don't want to make this go too long for you guys. I mean, it needs to be, it's a 5 credit hour class, but I don't want to make it any longer than the time that we're allotted. All right, example 2. By the way, I was going to record this lecture right after class on Wednesday night, but then when I sat down and looked over my notes again, I just wasn't very happy with what I had set out to do. So I rewrote everything, and now here I am sitting down on Thursday night doing this for you. Not sure when you're watching it. So this is the integral of 1 over the square root of 16 plus 4x squared dx. I also just came back from a 5-mile run like 20 minutes ago. And once again, I'm just sitting here in my own sweat. It's disgusting. I'm really glad that that's not going to be happening next semester. Okay, wonderful. Note the form that you're in. And by the way, some of you guys might be thinking like, well, is this really a trig substitution problem? Because the square root is in the denominator. Doesn't matter. It does not matter if your square root's in the denominator. What matters is that you have this form somewhere in your integral. It doesn't matter what else is in there. If you have this form, that's leading you to think like, okay, this is a trig substitution. So this is the form we have because we have a plus sign. That can only be this one. Okay. So your form is going to include the square root of a squared plus u squared. Now, you also need to match this up and make it fit this form. So what I mean by that is we need to make sure that we know what a and u are. What students tend to do here as a very common mistake is they say that u is like 4x or something. I think that's what happens a lot. But remember that u is the quantity that's being squared. So in this case, if a squared is 16, then a is 4 because 4 is the quantity that's being squared. And we can rewrite 4x squared as the quantity 2x squared, because remember, we need that whole quantity to be squared in order to say that we have u squared. And that means that u is actually going to be equal to 2x in this case. And that happens sometimes, no big deal. Okay, so remember that when we are in this form, we're going to let u be a tan theta. And we're going to let the square root of a squared plus u squared be a secant theta. You're probably going to do enough of these that you feel like you remember what the substitutions are. That's totally fine. You might want to just double check just to make sure that, that's the last thing you need is like, oh, shoot, I thought it was, I don't know, cosine when it was secant or something. So, you have the notes at your disposal. You might as well just check them. All right, so let's fill out what we have so far. We're going to let u be a tan theta. So that means 2x equals 4 tan theta. And remember that even though we don't actually need x in our integral, we don't have an x anywhere just by itself. We do need a dx. So we're going to go ahead and solve this for x so that we can get dx. So I'm going to say that x is 2 tan theta when you divide both sides of the equation by 2. And we're going to need the dx. So let's go ahead and take the derivative. So the derivative of tangent is secant squared. And don't forget your d theta, because we can't integrate without a d something, our variable of integration. I know some of you guys did that on your test, but you actually can't do that. It's a very common problem, people forgetting to write their dx's or their dy's. I might have filled them in for you on the test. When I was in Calc 2, my teacher took off points if we didn't write our dx's and our dy's and our d thetas. He also took off points if we graphed and didn't label our x and y and z axes. You guys think you have it bad. All right. Just reminding you of how good you have it in this class. In case you're feeling down, which sometimes happens at this point in the semester. Okay. Now we need to go ahead and make the substitution for the radical. So we are going to go ahead and say that 16 plus 4x squared under the radical is 4 secant theta. All right, I'm going to put my substitution cheat sheet away because I've used it now. And the next thing I need to do is just plug everything in and integrate. It all seems so simple, right? We'll see. Actually, this one's not that bad. Okay, so start out with your integral. If you would like, you don't have to. You might find it easier to write your dx in the numerator versus writing it off to the side. I'll leave that up to you. So we'll have 2 secant squared theta d theta. There's your dx. And then in the denominator, you have your radical, which is 4 secant theta. And then you're going to simplify. So 2 over 4 is 1/2. And then you have the integral of cancel out a factor of secant, and you have secant theta d theta. Now, I gave you a formula for the integral of secant u du, and that's going to be ln secant u plus tangent u. So 1/2 times the natural log of the absolute value of the secant of theta plus the tangent of theta. Technically plus c. If you pop it on at the way end, it's not a big deal. If you don't want to carry it around to each step, that's fine. Now, if you get this far, that's good. you've gotten probably more than halfway there. I would say you're 2/3 of the way there at this point. But what you need to do now is back substitute for x. So originally I was asking you to evaluate this integral in terms of x. You have integrated in terms of theta, but we know that x is not equal to theta because we have this substitution here. So we're going to rewrite secant theta and tangent theta in terms of x. Now, the secant of theta, we can pull from right here. We're just going to divide both sides by 4, and that gets you to the secant of theta. The tangent of theta, we're going to pull from right here. So I know that x equals 2 tan theta, so x over 2 equals tangent theta. So when I back substitute, my secant theta is the square root of 16 plus 4x squared divided by 4. And for my secant, I have, or I'm sorry, I just did secant. For my tangent, I have x over 2. And then plus c. Now, technically, I'm okay with this. This is fine. However, you might find that, especially if you're doing problems from the book and you're checking your answer in the back, that they're not going to list their answer like this. And you're going to know that because anytime you're taking a natural log and inside the natural log argument, you're adding or subtracting such that the numerators are constants. What they do is they kind of simplify this down. So I'm going to show it to you so that you've seen it, but I want you to understand that I'm okay with you leaving it unsimplified. It's sort of in the eye of the beholder whether or not this is simplified. But basically what happens is, to simplify this, you would get a common denominator, which would be 4. So you would still have a denominator 4 here. And then to get the denominator 4 in the second term, you would multiply each piece, the numerator and denominator, by 2. So 2 over 4 is the same as 1 over 2. Okay, fine. And then what they do is they use that rule that says, I'm going to remind you of what the rule is. The natural log of a over b is the natural log of a minus the natural log of b. So what that means is that you can say that this is 1/2 times the natural log of the absolute value of 16 plus 4x squared plus 2x, and then minus the natural log of the denominator. However you want to do this, you might. I'm going to just distribute the 1/2 actually. So that's what I will do. So minus 1/2 ln 4 plus c. And then using this identity for logarithms, if you get this natural log of a constant, well, the natural log of a constant is also a constant. And since c can be any arbitrary constant, sometimes they'll call this like c sub 1, and then they add this in, and they still call it c. So a constant is still an arbitrary constant no matter what you add or subtract from it. So this would just become 1/2 ln square root 16 plus 4x squared plus 2x plus c. So that would be the simplified way of writing the same thing. And technically, actually, I have in my notes here that this can actually be further simplified, which is true. But you don't have to worry about that. Yeah, because some of you might have been like, well, technically we could factor out a 4 and then take the square root of 4 and simplify. I mean, yes, technically there's more you could do here. I don't want to get too carried away though. This is fine. This is a variation that's closer to what you might see in like the back of the book. They probably wouldn't leave it like this or like this. They would leave it like that. So I don't want you to be confused and wonder like what happened to the denominator? Where did it go? Didn't really go anywhere. Okay. Example 3, as you can probably guess, I'm going to do the third and final form for this one. So this is the integral of, and then we'll have dx divided by x squared times the square root of 9x squared minus 1. Okay, so we are in form 3 here, if you're looking. This is a function of x squared minus a constant squared. So this is u squared minus a squared, u squared minus a squared. So we're going to let u be a secant theta, and then we'll let our radical be a tangent theta. So opposite of what we did last time. But again, we need to figure out what u and a are. So we would say u in this case is actually equal to 3x, because you have to, in order to get 9x squared, you square 3x. So if you want to think about it that way, just, write that extra step so you can verify. But if you take 3x and multiply it by itself, you will indeed get 9x squared. A is 1 in this case. The square root of 1 is 1. Okay, so let's go ahead and set up the substitution. I'm going to let u be a secant theta. And I'm going to let my radical, u squared minus a squared, be a tangent theta. And again, I am going to put away my cheat sheet because now I don't need it anymore. We hope. Okay. Wonderful. So let's go ahead. U is equal to 3x. So we're going to let 3x be equal to a secant theta. So that's 1 secant theta. And then remember, we're going to need dx. And actually, in this integral, we're also going to need x squared. So you really will need x in this case. You just don't need 3x. So we'll say that x is 1/3 secant theta. Might as well find dx. I tend to do that right after I find x so I don't forget about it. We're used to kind of doing that anyway, though. So dx, remember the derivative of secant is secant tangent. So we're going to go 1/3 secant theta tangent theta d theta. Okay, so there's your dx. As far as my radical is concerned, I'm just going to write this as 1 tangent theta. So just tangent theta. All right, well, let's pop this back into the integral and see what happens. You just never know what you're going to end up with. And we hope it's nothing too crazy. Okay, so you have a dx. That's got to get subbed out. You have 1/3 secant theta tangent theta d theta. Don't forget that. Divided by, in the denominator, you have x squared. Well, we know that x is 1/3 secant theta. You just might want to write that out twice or as 2 separate factors instead of writing it as a quantity squared. I don't know. That's up to you, but that's just my preference in this case. And then our radical is going to be tangent theta. Oh man, I'm kicking myself for not getting another color of writing utensil. Oh well, either way, cancel out what you can, and that's going to happen quite a bit with these trig substitution problems. Like for instance, 1/3 secant theta, there's one of them, there's one of them, done. I also have a tangent theta and a tangent theta that I can cancel. So let's see what we have left here. In this case, we have 1/3 in the denominator. Remember, when you're dividing by 1/3, you're multiplying by 3. And then you'll have d theta over the secant of theta, or 1 over secant theta d theta. You know what? If you find that easier to see, which you might, you can write it like that, because sometimes just seeing d theta over secant theta, it's not registering, but a lot of us will recognize 1 over secant theta as cosine theta. So that's what you're going to need to do here. I don't want you to get confused and think like, okay, well, if there's, for instance, last time we use this formula. Maybe I can do like 1 over this formula, or try to turn it into an inverse secant or something bizarre like that. Turn it into another trig function if you can. This one is easily converted to a cosine. Okay, so now that you have your cosine, integrate. The integral of cosine theta is sine theta. And then you're just going to sub out for sine theta. So this is another instance where I don't want you to freak out because you're like, oh man, I have to do trig. Technically, you really don't have to do trig. I'm going to show you why in a second. But notice that you don't have sine theta in your definitions. You have secant theta, you have tangent theta. So I personally find that the easiest thing to do in this instance, if you don't have the function already up here solved, is look at your triangle. That's what I would do. Your triangle in this situation is set up like this. So you have U on the hypotenuse, A on the adjacent leg. Let's do that. U we said was 3x. A is on the adjacent leg. And then your radical, U squared minus A squared, is on that opposite leg. Remember, your theta is down here. So now this matches the setup that we had for this triangle. Just use the triangle to figure out what sine theta is. So remember that sine theta is the opposite over the hypotenuse. Now, some of you I know are like, wait, I haven't had trig in like 5 years. I didn't remember that. Well, you're in luck because it's open book, open notes, and you have a trig handout at your disposal, and this is on it. So if you're not sure what the reciprocal function should be, or the definition as far as your triangles are concerned, feel free to look at that trig sheet that I put on D2L for you. Okay, so the opposite over the hypotenuse, if this is theta, the opposite of theta is over here, the square root of 9x squared minus 1. And the hypotenuse is 3x. Oh, not plus 1 minus 1, yikes. Not the end of the world, but it would have been if you tried to enter it wrong on achieve. Okay, so there's that. So we can now say that we have 3 times the square root of 9x squared minus 1 divided by 3x plus c. Cancel out your 3's, and that leaves you with the square root of 9x squared minus 1 divided by x plus c. And that is the integral right there. Excellent, excellent. That was example 3. All right. Sorry, I'm having issues here with my trachea. Unfortunately, when I pulled my notes apart and redid them the other night, I did not actually like rewrite a bunch of them onto a new sheet. I just made a lot of crazy notes to myself and smashed them all on here. So it's just taking me a second to remember where everything is and its location on my guide. Oh, this goes down here. Okay, so example 4. This one is not going to look like a traditional trig sub problem, but it is, and you're going to see very quickly that it is. So this is going to be the integral of 1 over 16 minus x squared. Hopefully we're already thinking about what form we're going to be using, to the 3/2 power dx. This is a 3/2. Sorry, that 3 looks almost 5-ish, but it's definitely a 3. Okay, now I want you to remember that a 3/2 power is the power 1 1/2. 3/2 is 1 1/2. So that means that you can rewrite this by saying it's the integral of, you might want to put your dx in the numerator. That sometimes is helpful with trig sub problems because you don't want to forget to sub it out. You might want to rewrite this as the square root, so the 1/2 power of 16 minus x squared times, and then just 1 power of 16 minus x squared. So these two are equivalent expressions. If you see a 3/2 power, don't freak out, just rewrite it. If you see that this quantity is being squared, well, that's fine. Just you can write the square root to the 4th power and do it that way. Either way, you're going to want a radical here so that you can work on this. Another way that you could write this is by saying that this is dx divided by, and remember, I'm going to remind you of your algebra rule here. If you have a to the m over nth power, you can rewrite this as the nth root of a to the m, or you can rewrite it as the nth root of a to the m. And you might find that this is a more helpful way of writing this expression. So instead of saying it's 16 minus x squared to the 3/2, if you want to write the whole thing as a radical and then cube it, you could do that too. So 2 is your denominator, that's your index. So we would say that this is the square root of 16 minus x squared, and then that quantity is being taken to the 3rd power. So it's kind of up to you how you want to do that. This might be a little bit easier just because it might not always be a 3/2 power. Like I said, sometimes you'll see this just being squared, and then it doesn't really look like a trig substitution. Sometimes these can be in disguise. And that's what chapter 7 is all about, just learning the techniques, looking for different things. It's not necessarily that each section itself is that hard. The problem is synthesizing it all when your test comes and understanding what technique to use. For instance, when I give you homework on trig substitution, you know you're supposed to use trig substitution and you apply trig substitution. But if I just give you this problem on a test, you have to look at it and determine, like, what do I use here? Do I use integration by parts? Do I use trig substitution? And then there's more stuff that we're going to learn after this with methods of partial fractions. And you're going to need to know, do I need to do that? Do I just do a straight up u substitution from Calc 1? Does this fit another Calc 1 integral like an inverse trig function, which we're going to be talking about more in 7.4. So that's really the trick to chapter 7. It's not that each section itself is that necessarily that hard, even though you will find that each section is challenging. It's being able to pull it all together in the end. So, all right. So you might want to write it like this as a radical, since you're going to need that radical anyway. So we are in the form a squared minus u squared. We're going to say that a equals 4. And u is going to be equal to x. So that's kind of nice in this case. We don't have a constant on your u squared, so you don't have to worry about, like, oh my gosh, did I forget that? We're in the first form that we did. So the first form was the square root of a squared minus u squared. And that was the first example we did. And in that case, we had u equals a sine theta. And then we let the radical a squared minus u squared be equal to a cosine theta. So let's go ahead and fill that in now, figure out what we're dealing with here. So we'll have x equals 4 sine theta. And then remember, we're going to need a dx because that's going to have to get subbed out for cosine theta d theta. All right, and then for our radical, we have the square root of 16 minus x squared equals 4 cosine theta. Now we can go ahead and start subbing it out and see what we end up with. So we have the integral of dx, which is 4 cosine theta d theta, divided by, and then we have our radical, which is going to be 4 cosine theta in our case, and we're cubing it. Everything's getting meshed together here. Well, cosine theta, quantity cubed. Okay. Now, if you would like, since we're going to have to simplify this out anyway, you know that one factor of 4 cosine theta is going to cancel out between the numerator and the denominator. So you can take out the 4 cosine theta in the numerator and take away one of them in the denominator. And now you have the integral of d theta divided by 4 cosine theta squared. And in that case, you might decide to write it out like this. You might decide to put it back together again. Sometimes it's helpful just to kind of see what you're dealing with here. Okay. The 1/4 times itself, or you might say the 4 times 4 in the denominator, you can pull that out as 1/16. Then we have d theta. In the denominator, you might want to write that as cosine squared theta. Don't panic. This is not a u substitution. Can't do that because I don't have the du in the numerator. You don't want to turn this into 1 minus sine squared theta because, again, where are you going to go with that? Nowhere. What you can do, however, and it might not seem obvious to us because I feel like, especially in trig, you're taught so often to work everything into sines and cosines that you don't think about doing it the opposite direction. But switch this from a cosine squared to a secant squared. Now, even if you're not sure where you're going, use some identities and kind of see what you might turn this into. You're not going to see any sort of crazy identities here. This is pretty basic for a reciprocal function. And if you're kind of like, okay, how does this help me at secant squared? Don't freak out thinking that you need to go back to 7-2 and use trig methods, because the derivative of tangent is secant squared. This is one of those integrals that's actually on your integrals and derivatives sheet that I put on D2L. The integral of the secant squared of theta, d theta, is the tangent of theta. All right, so that's our integral written in terms of theta. Now we'll back substitute to get this written in terms of x. Now, even though you don't have actually tangent theta up here, you can use the fact that tangent of theta is sine theta over cosine theta. So you can write this as 1/16, and then take your sine theta, which is x over 4, and then divide that by cosine theta, which is the square root of 16 minus x squared, divided by 4 plus c. Now, don't leave it like this. This is a complex fraction. It looks terrible, and it's not simplified at all. But when you invert and multiply, these 4s are going to cancel. So you're going to write this as 1/16, and then the x stays in the numerator, and the denominator stays square root 16 minus x squared, and then plus c. And I don't know, personally, I feel like you can leave it like this. This is fine with me. I don't see Achieve having a problem with this either. I would assume this would be fine. I mean, I guess the only alternative would be just to multiply the 16 into the denominator like that. I mean, this is also fine. But this is okay. I know normally I don't like when you write your answer as 2 factors, but really the difference between these two to me is very minute. Okay. Referring to my other resource here for example 5, which is the last actual trig substitution example I have for you. But like I said, we will do some more trig substitution in 7.4, which is kind of hefty. Okay, I might need a little more space. I'm giving you that look too when I say that. That means that this problem's, I mean, it's not super long. It's about as long as this one maybe, but I don't have enough room on this paper to write it. Don't freak out. It's okay. All right. Example 5. Right? 5, yes. Example 5. So we're taking the integral. This time I'm going to give you a definite integral. I've been kind of lazy about assigning these definite integrals and going through them. I just haven't really thought about it in some cases, just popping those limits on. But we're going to do it in this case. Oh, wait, is this the one I wanted to do here? Oh, no, I picked the wrong one. Never mind. Never mind. I do want to do a definite integral. This one is coming in 7.4. Sorry. Okay, so we're going from 0 to 1/3. That's right. Oh, I actually have it written down here. You know, I would rewrite this whole page, but by the time I do that, they're going to switch the book on me again, and I'm going to have to rewrite everything anyway. So that's what we're doing. 0 to 1/3 dx over 9x squared plus 1 to the 3/2 power. Okay. So now we already did one that looked kind of like this, and we talked about rewriting this as the square root of 9x squared plus 1, and then cubing it. If you find that to be the most accessible way to do that, then be my guest. The plus variation on this leads us to say that u is going to be a tangent theta. In this case, u is 3x. We've done one kind of like this before. And then a equals 1. So u equals a tangent theta. And then x is 1/3 tangent theta. Dx is 1/3 secant squared theta d theta. Okay. Now, if u is a tangent theta, then your radical is going to be a secant theta. Now let's go ahead and make the substitution, and then we'll talk about just applying those upper and lower limits of integration to your substitution. Okay, now I'm switching this integral to theta. It used to be in x. Now that technically means that we could switch the upper and lower limits of integration right now to theta, or you could back substitute and then use your original limits. Personally, I feel like back substituting is the least confusing thing for my students. So, I mean, you're essentially applying the same process regardless, but I'm going to do back substitution right now, and then maybe I'll change it in a later example to switching the upper and lower limits to theta. So for right now, if you want to keep your limits on there just because you don't want to forget to eventually apply the FTC, you might want to write them as x equals 1/3 and x equals 0, so you don't get that confused with your theta variable of integration. That would be my suggestion to you. If you decide to keep them, you need to make sure you note that they're x limits and not theta limits. But up to you. All right, so our dx is 1/3 secant squared theta d theta. And then in the denominator, your radical is being cubed, so that will be secant cubed theta. So I have 1/3 times the integral from x equals 0 to x equals 1/3 of 1 over secant theta d theta. And then again, you can write this as cosine. Now go back and switch this over. Oh, sorry. I don't mean go back. No. We haven't actually integrated yet. Hold on. We have to integrate first. I'm getting ahead of myself here. Okay. All we did was use the reciprocal identity to rewrite the integrand. Let's integrate. Okay. So we have 1/3 sine theta, and we're evaluating that from x equals 0 to x equals 1/3. Okay, but I don't have any x's, I just have thetas. So when we do this, we're going to have to switch this back over to x by back substituting. So what you are going to do in that case is rewrite sine theta in terms of x. And again, you can just reference your triangle. So we had the situation, to remind you, from page 1 of a squared plus u squared under the radical. And when you have that, your hypotenuse is going to be that radical. Your adjacent leg is a, and the opposite is u. The adjacent leg is a, the opposite is u, and then the hypotenuse is the sum of the squares of each side, of each leg, using the Pythagorean theorem. Sorry, I keep moving my pages around. So sine theta is the opposite over the hypotenuse. So 3x divided by the square root of 9x squared plus 1. And now that is going from 0 to 1/3. So we're now evaluating this expression for our values of x. So if you want to simplify first, that's fine. Not a whole lot to do here, but we will evaluate this now using the FTC. So we'll have 1/3 divided by the square root of 9 times 1/3 squared plus 1 minus, and then when we evaluate this at 0, we'll actually just end up getting 0 in this instance. So we'll have 1/3. So when I write the 1/3, though, I'm going to write the 3 in the denominator. The square root of 1/3 squared is 1/9. 9 times 1/9 is 1. So 1 plus 1, which is 1 over 3 times the square root of 2. And you don't need to rationalize in this class. I know that you did for trig. You've probably found out by now that achieve does not require you to rationalize your denominator, and I don't require you to either, not for calculus. If you wanted to rationalize, you could multiply the numerator and denominator by the square root of 2. And if you did that, 3 times 2 in the denominator would give you 6. Wonderful. All right. I'm actually going to stop because I'm getting tired and I still have 6 more examples and there's just no way I'm going to get through this tonight. So all hopes of a seamless transition are gone, but I'm going to stop this and hopefully I'll figure out how to splice these two together. Otherwise, you're getting 2 separate videos. Either way, this was 50 minutes approximately of trig substitution, and then I'll finish out 7.4 in another installation for you, which of course I want you to watch by Monday, which is the okay. Right now we're going to talk about section 7.4, And section 7.4, even though a lot of these integrals look extremely similar, you're going to find that very minor subtle differences between the integrals will make a huge difference in the way that you choose to solve the integral. So my goal here today is not only just to show you examples of techniques, but I really want you to understand when you might use one technique over another. I also want to impress upon you the fact that you don't necessarily have to choose one method versus another. It's possible that for some exercises, you're going to be able to use more than one method to find the value of the integral. Sometimes when I write a test, I plan for you to do a problem a certain way, and maybe it doesn't work out the first time. So I end up redoing the problem and rewriting it. And then I'm like, oh, this is perfect. This is perfect. This is going to be a great problem. And then someone will go and solve it a completely different way. And what happens is in the process of me actually writing the problem, I don't anticipate when I make little changes that I'm changing the possible solution process of the exercise. So I don't want you to feel like, well, I would have done it this way. Why would this work over that? Because in some cases, you have more than one method at your disposal. Most of the time, for what you know right now, you're going to have to use one way or another, but not in every case. All right, so 7.4 is officially called integrands containing ax squared plus bx plus c. Oh, not equals 0. This is not an equation. I meant to say where a is not equal to 0. Otherwise, you wouldn't have a quadratic. You would just have a linear expression there. Okay, so I also need to remind you of some Calc 1 formulas that you probably haven't used in a while, and I'm actually really glad I split this up into another day because last night I could not find my integration review notes that I gave to you. I believe it was the first lecture I ever recorded for you, maybe, where I had sort of an integration review. Does this sound familiar? Sorry, I've taught Calc every semester for like the last 4 or 5 semesters. And with summer, it's all bleeding together. And I can't remember what I did when, because summer wasn't that long ago. And I feel like, can I just do this? But I could not actually find that we had talked about taking integrals of inverse trig functions. So I want to remind you of what some of those integration formulas are, because you're going to see that they look really similar to some instances where you'd use trig substitution. So recall, and this is actually from section 5.5. So you had this in Calc 1. But if you had Calc 1 with me, we really got into this. Some teachers, I feel, kind of skate over this a little bit more. But if you had Calc 1 with me, we spent a lot of time talking about this particular topic. I know it doesn't seem like a lot of time because it was a summer class, if probably, or maybe it was in the spring. You had the integral of 1 divided by the square root of 1 minus x squared dx, and that was the inverse sine of x plus c. We have 2 more of these formulas. One is for if we had just 1 plus x squared in the denominator, and this is the inverse tangent of x plus c. And then the last one we didn't use quite as often, but it's still available to us. This one has x in the denominator, and then we switch the order of subtraction. And this is the inverse secant of x plus c. Now, if you're looking at these, you're thinking like, wait a second, these look really similar to these pieces that she gave to us for how to set up our inverse trig substitutions. Well, that's true. If you have, though, an exercise that just looks like this, you don't have to use an inverse, or I'm sorry, you don't have to use a trig substitution to actually evaluate the integral. If you have something where you just have a constant in the numerator and the square root of a squared minus u squared in the denominator, this is just in the form of an inverse sine. Now, when we did these in Calc 1, we spent a lot of time making sure that this constant was 1, because if the constant is not 1, then it affects the value of u. So if you remember, I made a big deal about saying like, okay, we're going to first focus on making this value a 1, because sometimes in your exercise, it might be any other constant. And then we kind of focused on writing u so that we could do a u substitution and rewrite it using our inverse trig functions. Now, one thing that you don't have for your inverse tangent is the square root. So I know we think about like, okay, well, we had a form that was a squared plus u squared. Well, that's true, but it was under a radical. So technically, you could consider this just being a radical squared, and then you could work this into a trig substitution. But usually these are a little bit easier to work out using an inverse tangent. Now, the big key here, and here's where I really want you to see the difference between this and something else we'd be doing, is the fact that you just have a constant in the numerator, and all this stuff is happening in the denominator. And again, with the inverse secant, we're switching the order of subtraction, and you also have this x out front. So this form is a little bit harder to attain just because a lot of times you don't have this x in front. So such is life. So you won't see this one quite as often. The inverse sine and the inverse tangent, you'll see quite a bit. So what I want to do here in 7.4, this is the section where I had made a big deal about saying you're going to have to complete the square. So hopefully, as I've been completing the square in a few lessons leading up to this here and there, you've sort of picked up on the process. But I'm going to be showing you how to complete the square again today. You should have learned how to do it in algebra, so this should be like a refresher. But what we're going to be doing is we're going to be rewriting integrals, and sometimes they're going to match this form. And you know what? If the x is bothering you, let's call it a u. I know now you're just like, what the heck? I just wrote this. It's not a big deal. I'm just going to switch these out to u's. Because officially, this is what we're going to be matching. Most of the time, we're not just going to have an x there. If we did, it wouldn't be a Calc 2 problem, would it? It would be a Calc 1 problem. And even then, you didn't see that a lot in Calc 1. Most of the time, you had some function of x. So maybe writing them like this will be helpful. You know why I wrote it with an x? Because that's what your book does. They always use x instead of u, and it drives me up the wall. But that's okay. All right, so we're going to be getting our integrals into these forms to start out, to use some inverse trig integrals. And then I'm going to show you some integrals where they might have parts of this, but maybe it's not necessarily an inverse trig and then we'll have to use a trig substitution. So I technically have 6 examples planned here. I don't think I'm going to be able to get through all 6 of them in the next 50 minutes, but that would be crazy because some of them are kind of long. So my guess is we're going to have to finish this up on Wednesday before we start up partial fractions, which is fine. That's really the way it's written on the schedule anyway. I've never been on a schedule like this. It's nuts. Okay, wonderful. Example 1. So example 1 is the integral of dx divided by x squared plus 2x plus 5. Now, like I said, whether the dx is in the numerator or whether the dx is off to the side is up to you. However, in certain forms, you might like better one way or the other. Whatever makes it easiest for you to see, do that. Okay, so you're looking at this and you're just like, I have no idea where to go with this integral. And hopefully you're not like, oh yeah, I totally know what to do with this. And then you do some weird power rule thing, which you can't do. This is something where before today, unless you remembered how to complete the square, you would be like, I don't know, I got nothing. So I'm going to show you how to do this. It's going to be wonderful. We're going to take this denominator and we're going to complete the square. Now, by the way, when I talk about partial fractions on Wednesday, and I know some of you are like, nope, too much information. Don't tell me right now. I want to wait till Wednesday. This is important though. So I really want you to understand the difference. When we're working on partial fractions Wednesday, you're going to see integrals that look like this. but they're most of the time going to have a trinomial that's factorable. This is not factorable. I can't take this and rewrite it as the product of two binomials. So I really want you to understand the difference between this and something that we're going to do in 7.5. So in 7.5, we're going to have a completely different solution process because we're going to have a denominator that we can factor into two binomials. This one we can't. So if you get a trinomial that you can't factor, you're going to automatically complete the square. And like I said, the reason Calc 2 is harder is because you have to kind of figure out what to do. You're not always going to, it's not going to be told to you automatically, like do this, do that, do this, do that. You're going to have this toolkit that you're going to use and just be like, I don't know, I'm going to try this, I'm going to try that. And it just comes with practice. It comes with seeing a bunch of exercises and just trying to get a sense for what to do when you see certain things. And when you see a trinomial, one of the things you're going to do is complete the square unless you can factor it. So that's what I'm going to focus on first. So I'm going to take the trinomial out for a second. So when you're working on completing the square, you're going to leave the constant by itself. And you're going to factor the first two terms, or I'm sorry, you're going to complete the square using the first two terms of this trinomial. So you're going to ask yourself, what number do I need to add to x squared plus 2x to make it a perfect square trinomial? And you're going to do that by taking half of the middle term's coefficient. The middle term's coefficient in this case is 2. So we're going to take half of 2 to get 1. And then whatever that number is, you're going to square it. 1 squared is 1. And then that's what you add to both sides. Oh, actually, I don't want to say add to both sides because we're not dealing with equations right now. So we're going to add and subtract this value. And you might be thinking, why the heck would we add it just to subtract it? Well, it's because I need it to be in here so that I can create 3 terms that are a perfect square trinomial, which now this one is. But when I add something to an expression, I've changed the value of it. So when I add it in, I must then take it away so that I don't actually change the value of the expression. Now I can rewrite this because I know that this is a perfect square trinomial. So you're going to keep the variable to the first power, keep the sign that comes in front of your middle term, and then you're going to add in half of the middle term's coefficient. So that's the number that you found here. And then you're going to square the quantity. And there are lots of crazy arrows going on now. Okay, so that's the number that goes in here. And then you're going to write what's left over. So 5 minus 1 is 4. So you have not actually changed the expression. Both of these are equivalent. You've just rewritten the way that it looks. So we've represented it such that we now have the sum of 2 squares. Now this might not always be a perfect square, but if it's not, we'll work on it. So go ahead and put your integral back together again. But now we're going to write our denominator as our perfect square trinomial plus 4. So x plus 1 squared plus 4. Okay. And then you're kind of like, okay, now what do I do? Well, look, you're now in this form where you have a constant in the numerator and your denominator is u squared plus a squared. Now, it's not a 1. We're going to make this into a 1 so that we can exactly fit the form. But we are going to let this whole term here be u squared. Well, you know what? I don't want to write u squared yet because we're actually going to change u as soon as we divide out that 4. But that's essentially what we're doing here. It's just this is going to be our variable term squared, and this will be, we're going to turn it into a 1. All right, so I want to match this form. So I'm going to make this a 1 to match the inverse tangent form. In order to make that a 1, I need to divide each term by 4. So I'm going to divide by 4 in the numerator. I'm going to divide this term by 4. And when I take 4 divided by 4, I get 1. So we divided each term by 4. And this should look really familiar to you from Calc 1. Divide each term by 4. Okay, so now one major thing we need to do here is this is a 1, which is what you want it to be. You want this term to be a whole quantity that's being squared. Well, right now, only the x plus 1 is being squared. So we need to rewrite this so it's an entire quantity squared. So I'm going to first pull this 1/4 out front just so it's not distracting me from the numerator. And then I'm going to rewrite the x plus 1 quantity squared over 4. And I'm going to do that by taking the square root of 4. So I'm going to take the square root of it and square it because I know that those two operations are going to undo each other. So I'm going to rewrite this as x plus 1 over 2 quantity squared. So try to be careful with your notation and parentheses here because you don't want to actually change anything. These parentheses include the whole thing. So I know that 2 squared is 4. I know that this exponent, when you take a quotient to a power, you're really taking that power to each piece of your fraction. And now you're ready to use your inverse tangent formula. So you have dx over 1 plus u squared, dx over 1 plus u squared. So you just need to go ahead and say now that u is equal to x plus 1 over 2. If you find that confusing, you can write it as 1/2 times x plus 1. And since you know you're going to need a du, if you find it confusing still, just distribute that 1/2 into your parentheses. You can do that also. Right, so there's your u, and don't forget that you need a du because we're going to have to sub out this dx if I'm going to rewrite the integral in terms of u. So my du in this case is just going to be a half. The derivative of 1/2. X is 1/2. Dx, the derivative of 1/2 is 0. So I need to write that. And then, of course, multiply both sides by 2, and you get 2 du equals dx. Okay. And now we'll just make our substitutions. So I still have this 1/4 in front. The dx becomes 2 du. In the denominator, we have u squared plus 1. And now we can go ahead and use that formula. 2 over 4 is a half. And then we know that the integral of du over u squared plus 1 is the inverse tangent of u plus c. And then go ahead and back substitute for x. So you can say now that this is 1/2 times the inverse tangent of x plus 1 over 2 plus c. So technically, this is like a Calc 1 problem. The only difference between this and a Calc 1 problem is the completing the square portion. So when you saw this in Calc 1, you didn't have 2 terms on it. U was always just like x squared or 2x squared, something like that. The square root of 3x squared. When you complete the square, you're going to end up with this binomial term so that u is just whatever this binomial term is. Okay, so the big takeaway here is you're not thinking trig substitution because there's no radical. And then when you go ahead and complete the square and work it out that way, you can just use your inverse trig formula. I mean, you could probably, no, I'm going to do this later just because, and I'll probably post it so you can see it. You could turn this into a trig substitution problem by writing your denominator here, x plus 1 quantity squared plus 4, as the square root to the second power. So I'm going to make a note to yourself. Make a note to yourself. Then you make a note to myself, but also make a note to you. You could try, if you wanted to, a trig substitution with the integral dx divided by the square root of x plus 1 squared plus 4 squared. I know I totally want to do this now, but I don't have time to do this right now, but I might work on it later and then kind of show you how you end up getting the same thing. But yes, you're essentially just taking this expression and you're just taking the square root of the square to undo it and turn it into the form that you would need. Because remember, for your inverse trig, for your trig substitution, I keep saying those interchangeably. For your trig substitution, you need a radical. So anyway, look for notes on that. It's probably a pretty simple trig sub problem. So it just would kind of come down to, what do I actually want to do here? So that was example 1. Example 2, I'm trying to just show you a bunch of different types of things here. Okay, so example 2 is the same idea. Again, if you took Calc 1 with me, you saw something like this. It was one of the last examples I did in the class because it comes really late in the book. So example 2, notice there's a huge difference between this and example 1. And you're just like, what do you mean there's a huge difference? They look so similar. It's true, they do look so similar. Look, example 1, dx over x squared plus 2x plus 5. Example 2, 3x dx over x squared plus 6x plus 10. Now, this is not going to be factorable, so you definitely won't be able to use partial fractions from section 5, which we'll talk about Wednesday. You're going to need to complete the square. However, if you're wondering what makes these two different, it's the x. This one, for example 1, has a constant in the numerator. Example 2 has a linear term in the numerator, 3x. This is not a constant. So even though there might be worked in here somehow an inverse trig function or an inverse trig form, it's not going to be clear to us right away because right now it looks more like just a standard U substitution. Okay, so note the difference. Note the numerator contains an x term, not a constant. That changes your thinking. That makes you think like, wait a second, this, even if I do complete the square, I'm not exactly sure where this is going to go. So I'm going to remind you, I'm going to take you way back when in Calc 1, and you might have seen something that looked similar to this in Calc 1. And you probably saw it in the natural log section, because notice that your numerator is 1 degree less than your denominator. Now, usually when you saw that from Calc 1, all you would have tried at that time would have been like, okay, well, let's let u be the denominator. You can do that. And then let's just hope we get the du that we want out into the numerator. So you would have said, okay, then du is 2x plus 6 dx. Like, okay, fine. Go ahead and factor this 2 out because we don't want a 2x. We don't have a 2x here. We just have a 3x. So let's go ahead and factor out the 2. That leaves you with x plus 3 dx. Okay, fine. We don't have x plus 3 dx. Divide by 2. And this is normally where in Calc 1 you would have been like, oh, awesome, I have an x plus 3 in the numerator. I'm good to go. But this time you don't actually have an x plus 3 in the numerator. What we can do is create a 3x dx, but you cannot get rid of this plus 3. It's there. It's not, you can't just And I made a big note about this in Calc 1. Sorry, it was only a few weeks ago for me. That's why it's so fresh in my mind. So I'm sorry if you did not have me for Calc 1. It's just, it was so fresh for me. I had mentioned in Calc 1, I'm going to mention it now. What I have seen students do is this. Oh, and it's so wrong that it's like weird to do. It's almost like I can't do it because it's so bad. I'm going to put a big no on this. I don't even know. They would do something like this, and then they'd be like, oh, okay, well then this must be 3x dx. And they would do this substitution using this information. You cannot do that with subtraction. You can only work on both sides here with multiplication and division. You can't just like take 3 off because it's not even 3, it's 3 dx. Okay, so this is like a big no, don't do this. I'm even just going to go like that because I just don't even want it displayed. Terrible. You cannot do that. You're not getting rid of this 3. You can't. But what you can do is you can force this to be at least a 3x, and then we'll sort of refocus ourselves and figure out what we can possibly do with this constant term. So we have a 3x dx. You can force this to be a 3x dx by multiplying both sides by 3. And you'll get 3x plus 9 dx. Fine. So if you're wondering like, okay, how does that help me? Well, I'll tell you what the situation is. You can do a u substitution, and you can force your integral to have a plus 9. But just like we did when we completed the square, if you add in the numerator, you must also take away that same amount. So this would be like best case scenario u substitution. So this is what you wish you had, but you don't have that. We have 3x dx, not 3x plus 9 dx. Make it yourself. You're going to make yourself a 3x plus 9 dx so that you can force this into a u substitution. Okay, we're going to force this to be 3x plus 9 dx so that we can use this substitution. But what we're doing in the process is creating another term. So we're going to keep our original, and here's how it's going to change. All right, so we're forcing the numerator to be 3x plus 9 dx, but we must also take away that 9. I'm going to do another problem like this in 7.4 also so that you can see this again because it is such an important technique. Okay, so we forced it to be here, but now you're like, okay, how does this help? Because we still have a minus 9. And all we really wanted was a 3x plus 9 dx. Well, no big deal, right? It has 2 integrals, you guys. Come on. Obviously, I'm just kidding. It's totally not obvious at all. Okay, the other one for the minus 9, I don't know. I mean, I'm just going to write this as minus. I'm going to leave this here so it's much clearer exactly where everything is, and we'll move it later in front of the integral. Okay, so we actually have not changed the integral. I'm going to zoom out a little bit so everybody can. There we go. All right, so we have not actually changed the integral. We still have 3x. We just added 9 and subtracted 9. 3x plus 9 minus 9 is still 3x. But now we've written it into two different integrals where we know how to solve the first one. So this one we know is a u substitution. So I'm going to say we know this one is a u substitution in a natural log form. It's a natural log form because you have du over u. We're going to, of course, just divide that 3 out, no big deal. But, or I'm sorry, 3 halves. But essentially, that's what you have there. So we're going to do this in two parts. And now here comes the question of, do I want to integrate this now and then come back to this? I think we'll just focus on this and then we'll come back to the integration here because we already kind of have a plan. This one is a trinomial in the denominator and a constant in the numerator. We just did a problem like this. This integral looks very much like the problem that we did in example 1. Where was it? Here it is. You have a constant in the numerator and your denominator is a trinomial. That's an inverse trig form. So your inverse trig form is going to be this one. It's because we have a constant in the numerator. Sorry, that says numerator. I don't know, you guys. Numerator with a trinomial denominator. Your inverse trig forms don't always have to look exactly like this. So sometimes you might not have a constant up here because you might have like x to the 4th plus 6x squared plus 10. And that would sort of change what your numerator would be. And that would still be a perfect square, but you're not really going to see that in this section. Okay. So now let's talk about the inverse trig form. So all this work with completing the square, we don't need it here. This is just a standard natural log. What we need to do now is focus on completing the square so we can get this into some sort of a squared plus u squared or u squared minus a squared or a squared minus u squared, something we're going to see when we get there. So let's go ahead and complete the square in the denominator. We have x squared plus 6x plus 10. Remember that we're going to complete the square on your variable terms. So you're asking yourself, what value would make this a perfect square trinomial? Well, you're taking half of the middle term, which in our case is 3, and then you're going to take that value and square it. And this is the value that you're going to add and subtract. So I'm going to add the 9 in to make my perfect square trinomial, but then I have to also take it away. All right, so when I rewrite this as a perfect square, I'm going to write this as x plus 3 quantity squared plus 1. So the 10 minus 9 gives me 1. And then to complete the square, I'm taking x plus, and then half of the middle term's coefficient, in this case, is 3. Okay. So now I can say that I'm looking at two different integrals. And now I'm actually going to write these as two separate integrals. So the notation gets a little funky here, and everyone's going to have a different way of figuring out how they want to write this. I'm going to just summarize this here underneath where we already have it. So we'll have 3x plus 9 divided by x squared plus 6x plus 10 dx minus 9, just going to pull that 9 out front, times the integral of dx divided by x plus 3 squared plus 1. This is going to be in the form of an inverse tangent this is in the form of your natural log du over u. Okay, so I'm going to look at each of these separately, and then we'll subtract one off the other. Just that's the way it's going to have to be. Your first integral, 3x plus 9 divided by x squared plus 6x plus 10 dx. Well, you actually already did the work for that one. It's all the way up at the top. Probably a faster way of zooming in and out. All that work was here. So what you learned in Calc 1 was if you're not sure what to do, especially if your denominator is 1 degree more than your numerator, just let u be the denominator. So that's what you did. You let u be the denominator, and you figured out that 3/2 du would be equal to 3x plus 9 dx. So you're going to take your 3x plus 9 dx and turn it into 3/2 du. And then just divided by u. Super straightforward, right? So that's just a Calc 1 thing right there. This is 3/2 times the integral of 1 over u du, which is where your natural log comes in. I'm going to write plus c just because it's hard for me to not write the plus c. Let's see, x squared plus 6x plus 10 plus c. Okay, this is like not our actual result, but it's like a sub result because it's the first integral that we were looking for. So this is for the first term. Now what we're going to do is we're going to integrate the second term, and then we're just going to subtract the 9 times that second integral from the first. There we go. Okay, so for your second integral, and you can keep the 9 on it if you want to. That's fine. Just don't forget you're going to be subtracting this from the second integral when you're done. Okay. So we have this. This is an inverse tangent form. I already have a 1 here. That's great. If I already have a 1, that means I can go ahead and just let u be whatever quantity is being squared. So we're going to let, oh, and you know what? This is going to make some of you very upset. I'm not going to use u. I'm going to use w just because it's really confusing that we already had a u up here for the first term. So I'm going to go with w. It's better notation, you guys. I don't want to go back and say, okay, let's back substitute for u and then accidentally use the wrong one. So we're going to let w be x plus 3. And then dw, my favorite character, is going to be dx. I already have the 1. So you might be thinking like, isn't there something missing? Don't we need to do more? Actually, this integral is going to be super straightforward. We've already done the work that we need. The hard part of this one was just rewriting it into the 2 different integrals. So this is going to be 9 times the integral of, well, the dx is dw. And then in the denominator, you have w squared plus 1. So this is just going to be 9 times the inverse tangent of w plus c, which is 9 times the inverse tangent of x plus 3 plus c. This is your second integral result. Now, to finish the problem, we're going to combine these 2. Again, I'm just going to rewrite this so you can see exactly where everything is coming from. I know so much rewriting, but I tell you, it helps to make things clear, I think. Okay, so we have gotten both of these quantities now. The first integral we found was 3/2 ln x squared plus 6x plus 10. Don't forget your absolute value bars. And then we're subtracting off 9 times the inverse tangent of x plus 3 plus c. Stick a fork in it. It's done. Oh, come on. Wasn't that fun? You guys, I love this. I love this. Part of the reason I didn't want to do this while I was so tired last night is because I really wanted to just savor it and enjoy it and not be like, oh, I'm tired. I'm going to trudge through this. Because I love this. Oh, wasn't that so fun? Satisfying? Okay, maybe not fun for you, but satisfying? Okay, to recap. We noticed that, first of all, this was not a standard inverse trig integral because of the x. The x was kind of leading you to think maybe it's a u substitution. So you let u be the denominator, and then you kind of worked your way through trying to match this up with what you had. You were trying to get 3x dx. You got 2x plus 6 dx. Then you, okay, fine, factor out the 2, divide it out. Now you have x plus 3 dx. Well, you wanted 3x. The only way to get that is to multiply both sides by 3. And remember, that's not 3x plus 3. You got to distribute that 3. So you have 3x plus 9 dx. So you were thinking like, okay, if I'm going to use a u substitution, I have to have 3x plus 9 dx. Well, I don't have 3x plus 9 dx. So I'm going to force it. So then you came down here and you said, all right, I got 3x plus 9. I'm going to make it happen. But if I'm going to add in 9, I have to also subtract the 9. And then you rewrote this into two integrals. Well, here's your u substitution, and this one is your inverse trig function. Okay, it's actually not my husband mowing the lawn right now. It's daytime. It's all the landscapers. I was just like, is he seriously? Why does he always mow the lawn while I'm teaching? Not him. He's off today. Okay. I don't usually like when he has days off. I tell him he needs to go back to work. He cramps my style. Okay. But he's washing my car, so he's good today. All right, so you wrote this in two integrals. You knew this was a u substitution. The other one, now you had a constant in the numerator. When you have a constant in the numerator and a trinomial in the denominator, you should be thinking inverse trig function. So you went ahead and said, okay, I want to complete the square to rewrite this in some sort of a squared plus u squared minus u squared minus a squared, something. You were going for something. You got that. Over here, you already had a 1. You're golden. No big deal. Everything's good. Okay. Like I said, we're going to do another one of these, like let's force our numerator to change things. But first, let's do one where you have some options. Options are good. I know you guys hate options. You're just like, why? Just give me one thing to do. No, that's not how it works, team. You got to know all the ways. Example 3. This is the integral of dx divided by the square root of 5 minus 4x minus 2x squared. This one's a little trickier because you don't just have x squared, you have 2x squared. I also want you to notice that this one looks like it could potentially match up with more than one form. You definitely are not thinking any sort of u substitution, because if you let u be your radicand, well, du would be negative 4x minus 4. Well, you don't even have an x up there, so that's not going to help you at all. If this was a constant, I'm sorry, if this was like x dx, then yeah, you'd be thinking, let's do a u substitution and try to write this as 1 over the square root of u, or du over the square root of u. But you have a constant. So this is leading you to think it's probably going to be an inverse trig function. And it's probably, if I remind you of your formulas, several pages back, it's probably going to kind of match this one. That's going to be my guess. Just because you're starting out with a constant and then the variable terms are negative, you're probably going to complete the square and get it into this. But you might also be able to, you will be able to do both, by the way, get this into a form such that you can use a trig substitution. You have some options here. Now, if you want to always default to trig substitution, anytime you have a radical in your expression, that's fine, because that one's always going to work. The problem here is that sometimes your inverse trig won't work just because you might not have a constant in the numerator, but that's not really a problem here. So you're going to be able to fit more than one method into this example. You'll have some options. The first thing you're going to do, though, is at least write this into some sort of a squared minus u squared minus a squared, whatever it ends up being. So I'm going to show you how to complete the square here. It's a little bit trickier just because you have a negative lead coefficient. I know it doesn't look like your lead coefficient, but it is. Okay, so let's take that out of the radical for a minute. And I want you to rewrite this in descending order. I think that's going to be the best way of doing this. Definitely write it in descending order. Okay, now, here's the part you have to remember. When you complete the square, you don't want negative 2x squared. You want x squared. So you're going to factor out the negative 2. But you're not going to factor it out of the constant term. You're going to leave the constant term alone. And you're not going to forget that when you factor a negative out of a value, you're going to change its sign. Remember, when you're factoring, you're dividing. So negative 4x divided by negative 2 is positive 2x. And then you're going to double check and make sure you did this correctly. Your 5 is going to come straight down. We're not factoring anything out of it. Negative 2x squared and then minus 4x. That one's good for right now. Okay, so we have this going on. The 5 is not going to change at all. We haven't factored anything out of it. Remember, your constant term you're going to leave for a second. What we're going to do now is we're going to complete the square inside the parentheses. So the negative 2 is going to stay right where it is. And I'm going to ask myself, what value do I need to add inside the parentheses to make that binomial a perfect square trinomial? And what I'm going to do is I'm going to take half of the middle term's coefficient, which is 1, and I'm going to square it, which is also 1. Your 5 is going to come down, and then you're not going to do anything until you account for this value that you added. And what you're not going to do is subtract 1, because you didn't actually add 1, did you? No. You actually added in negative 2. You have to consider the fact that when you factor out this negative 2, it still technically is going to get distributed into the parentheses at some point, and that's going to affect your expression. So you need to consider the fact that instead of adding 1, you actually subtracted 2, or you added negative 2. Negative 2 times 1, negative 2. So you need to account for that by adding 2 back in. I know, it seems weird. Negative 2 times 1 is negative 2. So add 2 back in. It's not necessarily hard. It's just you have to remember to do it. It's just you got to account for everything. Okay. Now complete the square. So the negative 2 comes down. Complete the square inside the parentheses, and you'll get x plus 1 quantity squared. 5 plus 2 is 7. Now, we don't have a form that's like negative something squared plus something. If this is a minus, then switch this to a subtraction problem. Otherwise, it's very easy to look at this and be like, okay, what do I do now? And I don't want you to think about this as being plus, because if one of your terms is negative, you want to switch that into a subtraction problem. You want this to be in the form a squared minus u squared. You don't want it to be in the form negative u squared plus a squared because it's going to screw up your substitution. Okay. Rewrite your integral. Dx divided by the square root of 7 minus 2 times x plus 1 quantity squared. And I was debating over whether to do this using a standard trig substitution or an inverse trig function. And I think actually the trig substitution is easier. We haven't done one yet today in 7.4. So I know technically I'm going to splice these videos together and you're going to be like, we just did one like 50 minutes ago. It's true. But it's a new day for me. Let's do this with an inverse, or I'm sorry, with a trig substitution integral. Okay. So I'm going to even make a note here. Can do a trig substitution or put in an inverse inverse sine form. Now, the only tricky thing about doing an inverse sine here is just, you know, when you make this a 1, the work gets a little bit algebraically heavy. The trig substitution is going to be a little easier. So let's do that. Okay. So back to your trig substitution from forever ago definitions. We have a squared minus u squared. So we're going to use this one where u is a sine theta and your radical is a cosine theta. And oh, by the way, if you're thinking like, we're not actually in a squared minus u squared, you would be correct. We're not actually in a squared minus u squared yet because we still have this 2 here. So we're going to have to fix this up a little bit more in order to get this into a squared minus u squared. Sorry, I totally neglected to consider that too. The 2 is not currently part of the square. We're going to force it to be part of the square. The 7 is going to stay right where it is. And if I want to make 2 a square, I'm going to take the square root of it and then square it. I haven't changed it now. The square root of 2 squared is 2. And then you'll have x plus 1 squared. And then you can use that property that says that the product, what is that? I'm going to write you an exponent rule, but I can't remember exactly the way that I was writing it. A to the n, b to the n is a b to the n. A product to a power is a product to a power is the, I don't know, I used to have like a lingo for this when I was teaching algebra. I remember. Anyway, you can distribute the exponents. We talked about this the other day. As long as you're multiplying, you can distribute the exponents onto each factor. Yeah, it's fine. You don't need the lingo, the fancy like this to the that name. It's eluding me right now. Okay. So let's go ahead and rewrite this now. 7 minus, and then I'm just going to, instead of having a squared times b squared, I'm just going to take a times b and square it. So we'll have the square root of 2 times x plus 1 squared. So little tricky there, just making sure that we get that into the proper form, but not really, it's certainly not calculus, it's algebra. It's just algebra. Okay, now we are there. We are in a squared minus u squared. We just looked at that trig substitution. We know that if we're in this form, we can go ahead and let u be a sine theta. I'm going to do that now. And u is going to be whatever that quantity is that's being squared. You're not used to having a u that has so much going on in it, but it happens, and that's okay. So there's your u. Now, we need to remember that a squared is 7. I should have actually written this down over here. I'll write that underneath. I want to make sure it's super clear here. Okay. So if a squared is 7, that means that a is the square root of 7. So very subtle, but very important. If u squared is, well, we already have a written squared, then u is going to be the square root of 2 times x plus 1. All right, so u equals a sine theta. So we have the square root of 2 times x plus 1 equals a, which is the square root of 7, times the sine of theta. Now, another tricky thing here is you have to remember that even though you don't actually need x in this integral, you don't have an x anywhere that you need to sub out, you are going to have to sub out your dx, and you're going to have some value for that. You can't get a dx without an x. So you're going to have to solve this for x so that you can get dx. To do that, go ahead and distribute. And you'll have the square root of 2 plus this, I'm sorry, the square root of 2x plus the square root of 2 equals the square root of 7 times the sine of theta. Then to get x by itself, subtract the square root of 2 from both sides. Now, this is not like a d theta situation yet, so we can add and subtract from both sides. I don't want you to think like, oh, well, she said we couldn't do that earlier. That was different because earlier we were talking about du's and dx's, and you can't work that way with those when they're being tagged on like that. But we're just solving an equation right now for x. All right, now divide each term by the square root of 2. The square root of 2 divided by itself is going to be 1. All right, so there's your substitution for that. We are going to need the dx. So the derivative of sine theta is cosine theta. The constant multiple gets tagged along. The derivative of 1 is 0. Don't forget your d theta. And then this one is on its way to being done. All we're going to do is sub this stuff back in. Okay, so here's our integral. So the dx is going to be root 7 over root 2 cos theta d theta. Oh, and I actually forgot to write the substitution for our radical just because it was so long. I think I was just avoiding it. Okay, so our radical is equal to a cosine theta. And again, that's just from your formulas that I gave you at the beginning of 7.3. So the substitution that you make here for the square root of a squared minus u squared is a cosine theta, where u is a sine theta. The radical is a cosine theta. I feel like this looks weird just because it's different. So if you're wondering where that came from, that's where it came from. I guess, I don't know. The benefit to teaching this class so often is that I hope that I'm properly anticipating questions students would have and where they get stuck and what's not obvious to them. Okay, so this is your dx that's up here in the numerator. We found it right there. And then in your denominator, this radical is just the square root of 7 cosine theta. And you might be wondering, like, did I do this wrong? This doesn't look right. No, it's right. The square root of 7s will cancel. You'll get 1 over the square root of 2. The cosine thetas will cancel. And now you just have d theta. Now, it's not 0 d theta. Otherwise, you wouldn't have an integral at all. It's 1 d theta. So the integral of 1 in this case is just theta. And now you just need to find theta. No big deal, right? Okay, so if we have, I'm going to go back to this substitution right here. The square root of 2 times x plus 1 equals the square root of 7 sine theta. We need to get a theta out of this. So I mean, it's kind of, we're going to get everything back in terms of x, whether you want to use it here or there. This might be the easiest way of doing it, the fastest way to isolate sine theta. Okay, so divide both sides by the square root of 7. And that will get you to sine theta. But we just need theta. So if you're trying to isolate theta, take the inverse sine on both sides. And that will get you to theta. So now you can say that you have 1 over the square root of 2 times the inverse sine of the square root of 2 over the square root of 7 times x plus 1 plus c. Oh, and that's going to be real fun to enter into Achieve, right? Such is life. Okay. I think I have like 5 more minutes. I have 5 more minutes. I know you're just like, stop the bleeding. I don't want this to stop because I love this so much. I'm totally bummed that I don't have more time. The one thing I was going to do really quickly with this one is just show you that you could also do this without a trig substitution. I mean, it's just an inverse sine integral, right? For example 3, I can do this in 5 minutes. With an inverse trig function, it's the inverse trig method, you can take your original, well, let's say take your original after we've completed the square. So it, yeah, because we do need it to be in the form of the square root of a squared minus u squared. So let's say you were back here, and then we had the square root of 7 minus the square root of 2 times x plus 1 squared. I'm going to just use the fact that I'm going to write it again just because it was a while ago. Du over the square root of 1 minus u squared is the inverse sine of u plus c. Again, we're super close. We have a constant minus u squared. You can just make this a 1 by dividing everywhere by the square root of 7. Just remember that your 7 is actually under the radical. So when you divide by 7 under the radical, it's still technically the square root of 7. It's just going to look different if you're doing it outside of or underneath the radical because it's already accounted for. But if you're going to take, you know what, I'm going to write it twice because I think that'll be most clear. I don't want people being like, what happened? What? And then racking your brain over it. Okay, so here's what I'm going to do. I'm going to write the dx. No, I'm not going to write the dx yet. I'm going to go with 7 minus the square root of 2, x plus 1, quantity squared. And then we're going to divide this by the square root of 7. And then I'm going to take 1 over square root of 7 dx. So I'm dividing by square root of 7 in the numerator and the denominator. And remember that I also have a rule from algebra that says that the square root of a over the square root of b is the square root of a over b. So this 1 over square root 7, I'm going to pull out front. The dx can stay right where it is. And then in the denominator now, I have 7 over 7 under 1 radical. And then the square root of 2 times x plus 1 quantity squared divided by 7 in the denominator. So just using this rule from algebra, instead of dividing by the square root of 7, just putting that 7 combining it as one fraction in the radicand. And that's going to help us make this a 1. So you're going to have 1 over the square root of 7 times the integral of dx divided by the square root of 1. That's what you were looking for. And remember, you want 1 minus u squared. So I want to make this a perfect square, the whole thing. If I'm going to do that, I'm going to have to take this and again write it as the square root of 7. So I can take the square root of 7 squared and get that 7 to come back. So I'm going to write this as minus the square root of 2 times x plus 1 divided by the square root of 7 quantity squared. So just, it's a series of little rewrites that you're doing, being very careful with your arithmetic just to get this so that you now have u equals the square root of 2 times x plus 1 divided by the square root of 7. If you feel more comfortable writing that as just a constant multiple fraction, that's fine. And then what we're working towards here is just being able to write this as inverse sine u plus c. So now you have a u. Your du, well, if you find it weird to see in this form, just distribute it, and you'll see that du is the square root of 2 over the square root of 7 dx. I really recommend keeping these split up in the fraction, these radicals. I think it'll help you to simplify. Usually that's just easier to look at. And if you're going to sub out your dx, well, we know that dx is going to be the square root of 7 divided by the square root of 2 du. So just multiply by the reciprocal on both sides. And then we can say we have 1 over the square root of 7 times the integral of dx became the square root of 7 over the square root of 2 du. And then in the denominator, you have the square root of 1 minus u squared. Now the square roots of 7 will cancel, and then you'll just have this guy. And we know, because I just put it up here, sorry, it's up here, that as long as I'm in this form, I have the inverse sine of u plus c. U was the square root of 2 over the square root of 7 times x plus 1 plus c. Now I'm going to zoom back out so we can match this up with the other method that we used here. Notice, oh gosh, I can't even zoom that far. This was our answer using just a standard inverse trig process, just by, making this guy a 1 and just sort of matching it up with our inverse trig form. And this was the answer that we obtained using a trig substitution from 7.3. So same exact answer. So for some of these, you will have options for the solution process that you want to use. So we did a lot in 7.4. I do have a couple more examples that I think will help, but they're really not that much of a departure from what we've done so far. But a lot of times I feel like seeing more examples, kind of seeing that repetition makes a big difference. So next time I do want to go over another problem where we're going to complete the square and use an inverse, or we're going to complete the square and use a trig substitution. And for that example, we're not going to have an option to just use this method. You're going to have an integral that has more going on with it, where you have to use a trig substitution. So I'm going to do 2 of those, and then I'm going to do one more example that requires you to force your numerator to be the way you want it to be, like I did in example 2. So just kind of saying like, okay, well, this is what I want. I don't have it. I'm going to make it happen. So we're going to do one more of those on Wednesday, and then we'll start up partial fractions. Okay, I'm so excited. You guys, I love this stuff. I'm really sad that eventually it will come to an end and we'll have to move on, because chapter 7 is my favorite of all the chapters. And maybe some of you guys are really enjoying this too, and others are maybe just like, oh, I missed chapter 6. I don't know what you like. Okay. Have a wonderful day. I don't know when you're watching this. I don't know if I should wish you a wonderful evening or what, but have a wonderful day, and I'll see you on Wednesday. I'll put up a little bit of homework to get you started on this, but it won't be due yet, so you have some time. Okay, I'm gonna stop this recording now. Bye.